Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 5. We're studying the structure of the atom, and we're on 5.3, Electron Configurations. So, except for the mass of the atom, virtually every property of the atom is determined by electrons, including the size of the atom and its chemical bonding, and a lot of its properties. Electron configurations determine the properties of atoms. So we're going to be talking about electron configurations because they are super important because they deal with chemical properties and we are in chemistry. So that's why we're going to study them. So electron configuration, please write this down. It is a description of which orbital contains electrons when looking at a certain atom, and it depends on the element. So we're looking at the element, we're looking at the energy shell, and we're looking at the orbitals. So I am going to have you make a simplified view of this periodic table. So you're going to sketch out a periodic table like this, and you're going to include these last two rows. And then I want you to label these two columns 1s, 2s, 3s, 4s, 5s, 6s, and 7s. And then way over here, helium is also 1s. And then there are 1, 2, 3, 4, 5, 6 columns if you want to put them in there. Otherwise, you could just make a block. And this is 2p, 3p, 4p, 5p, 6p, and then this would be 7p. And then in this middle block, if you want to put in the columns, you can. There are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it starts with 3D, 4D, 5D, and then 6D. And then you don't need to put all of these in there. You just need to make sure there are two rows. And the first row is 4F, and the second row is 5F. Now that you have that periodic table written, let's look at more about the electron configuration. The electron configuration includes the principal quantum number, the orbital, and the number of electrons. And the principal quantum number is usually the energy level or the row number of the periodic table. So one example of an electron configuration is 1s2. So from this information, we know it is in the first energy level or first row of the periodic table. And we know that the electrons are in the s orbital, and there's 2 electrons in that s orbital. So let's take a look at the periodic table. So we know that this element, this atom, is going to be in the first row, so it's either hydrogen or helium, and it's an s, so still only hydrogen and helium, and it has 2 electrons. So that would be helium. So this is the electron configuration for helium. Okay, so remember, electrons always settle into their lowest energy state. So you can't fill any energy levels or orbitals until all the lower ones have already been filled. So sometimes it doesn't always seem intuitive, so I want you to write down the diamond rule or the diagonal rule. And what you do is you go 1 through 7. So you want 7 rows and all in a column. So this needs to be done neatly so that it will work out. 1s, 2s, 3s, 4s, 5s, 6s, and 7s. And then you're going to make a second column and make sure the 2p is in the same row as 2s. You go 2p, 3p, 4p, 5p, 6p, 7p. And then a third column, and that's be your D column, and that'll start with the 3s, 3D, 4D, 5D, 6D. And then you will make a fourth column, the F column, 4F, and 5F. And now electrons fill, this is a neat little diagram, which if we do diagonals, it tells us how the electrons fill. And this can be a little cheat sheet for you. So it starts out, and you want to draw these arrows, 1s, and then it goes to 2s, and then after the arrow we always come back to the next one, and then it's 2p3s, and then it's 3p4s, and then it's 3d4p5s, and then it's 4d5p6s, and then 4f5d6p7s, and then 5f6d7p. All right, so let's practice that a little bit. All right, so looking at our 1s2, remember it tells us the quantum number is 1. That is our first energy level, or the first row in the periodic table. And then s is that s orbital. And then 2 means there are 2 electrons. So it'd be 1, 2. And that is indeed helium. Good job. And if we see, these energy levels and quantum states relate to the periodic table. So this is energy level 1. Energy level 2 has 2 orbitals, s and p. Energy level 3 also has 2 orbitals, s and p. Energy level 4 has 3. You've got s, p, and then d. And same thing for the next one. You've got s, p, and d. And then below that you add in another one. It's got the f orbitals. And that's the kind of boxes at the bottom. So electrons determine the shape of the periodic table, and electrons and their energy levels, excuse me. And they always settle into the lowest unfilled quantum state. So I'm going to have you start writing some electron configurations. So looking here, I'll give you a hint. We know helium was 1s2. So hydrogen, please write hydrogen's electron configuration. If you said 1s1, you would be correct. Good job. All right, so now I'll do lithium, and then maybe we'll take a guess and then we'll go over them together. So lithium, you have to write what went before, so that would be 1s2, and now we're in the second row, so that's 2, and this is s, 2s1. So please write down lithium and 1s2, 2s1. Coming over to fluorine, remember we always have to write what came before, so that would be 1s2 and then 2s2, because we see this one is, our little s orbital is filled, so 2s2, and then we write 2p, 1, 2, 3, 4, 5, 2p5. So please write fluorine, 1s2, 2s2, 2p5. Okay, so I'm going to have you try sodium and neon. So sodium, you want to see is going to end in the third energy level and the s orbital. See if you can get that one. And neon, we see ends in the second energy level and the p orbital. So see if you can get that one. Okay, you want to make sure that you have a periodic table, and I want you to write the electron configuration for silicon. And then I want you to try writing the electron configuration for lead. After you've written the electron configuration for lead, you will probably realize that it would be great if there was a shortcut, and indeed there is. Noble gas notations are the shortcut, and they can be quite useful. So please write this down. To do the noble gas notation, you find the last noble gas, and you put a bracket around its atomic symbol, and then you do the rest of the electron configuration after that. So for example, you're going to write the noble gas notation for silicon. So the noble gas that comes right before silicon is neon. So we're going to put neon in brackets, Ne, and then we're going to do the rest of the configuration. So after neon, we go to the third row, so that's 3, and that's 3s2. And then we go over to the p orbital, so that's 3p, and it's not filled, there's only 2 electrons in it, so it's 3p2. So we get Ne in brackets, 3s2 and 3p2. Okay, very good. Now I want you to try writing the noble gas notation for lead, and we'll go over that in class. All right, so looking at our electron configuration for silicon. So we know that there are 14 protons in silicon, and we know that since it's a neutral atom, there are going to be 14 electrons. So we know if you have our electron configuration chart, it's just, the diamond rule written out in a line. So 1s2, 2s2, 2p6, 3s2. So we've got 2 there, and then 2 more is 4, and then 6 more is 10, and then 2 more is 12. Well, it's somewhere between this one and this one. So somewhere between 3s2 and 3p6. So those last 2 electrons out of 14 need to go in the 3p orbital. So that leaves us with 1s2, 2s2, 2p6, 3s2, and 3p2. So looking at our energy levels and then our orbitals, we have 1s is filled for silicon, 2s2 is filled, 2p6 is filled, then we have 3s2 is filled, and then we have 3p2 to get to 14. And then if we were to go to a different element, we would go to the 4th, the 5th, 6th, and so on quantum numbers, principal quantum numbers. So here's a periodic table showing which orbital typically contains the highest energy electrons. So this is a blown up view of what we wrote down at the beginning. And if you find this easier to use, go ahead and make this chart, but I won't make you make the chart. That concludes our 5.3 electron configuration notes, and we will get a chance to practice that in class. All right, thank you very much.